Okay, so with that, so this is the exam 3 review for Organic 2. So with that, spring 2016. So with that, we're going to go over the review slides. So with that, so there's going to be two mechanisms that you guys see. So with that, so you're going to have one of these, so electrophilic aromatic substitution, or the carbon version of it, the Friedel Crafts. So with that, including the alkyl hydryl shifts. So take a look at those. So with that, so mechanisms from the notes. So with that, so the other thing you can do, the other mechanism you're going to see is hydration of aldehydes or ketones, either the base catalyzed or acid catalyzed ones. So with that, so for the electrophilic aromatic substitution, right? So with that. Okay, so remember they all work the exact same way. Okay, so with that, so you have. So let's say we're adding this plus, BRBR to get like this, FeBr3. Okay, so remember they all work the exact same way. Okay, so with that, so remember you've got lone pairs here. Okay, so these guys, so the bromine is going to attack there and grab those to form this Br, right? Because these electrons here have gone with that bromine, right? Br plus, okay, and FeBr4 minus. Okay, now we have negative character here. You've got something positive, right? So this is going to attack there, right? I'm going to draw these hydrogens just so you don't forget. So you're going to end up with this, right? So like that. Bromine's on one side, the positive is on the other, just like normal, stuff like that. So, right? So with that, so and then this guy's going to attack that. Oops, not that one. Sorry. It's going to attack that one, collapse down to give that. Stuff like that. So that's your mechanism. That's how all of these work. You got to make something positively charged. The benzene attacks, and then this comes back and rips off a hydrogen from where you've added. Stuff like that. So it doesn't matter. Friedel Crafts works the same way. You have something that's a positive charge on a carbon. Right, so with that, the bromine or the benzene attacks there, and then this thing comes back, rips off a hydrogen from where you're from where you added. Not too bad. Okay, so for the right, so with that, so for the acid base mechanism, right, so you're going to have something like this. We'll do the acid because it's a little bit more difficult. Here, well, let's do them both. It's be easy. Okay, so you have H2O and then OH minus catalytic. Okay, and you're going to end up, I'm going to give this to you. OH. H. Okay, so this oxygen is from here. This oxygen is from here. Okay, so like that. So, okay, so remember these things. Positive, negative, right? So. Right, oxygen's more electronegative, right? So it's here and here, right? So this negative charge is going to attack there, push that up. Right? Oh, forgot to draw the lone pairs. Right, so you're going to end up with this. This negative charge here. Oh, excuse me. It's an OH minus, okay? Now this is going to attack one of the waters. Remember, the water is HOH. That's going to grab that, move this away, and you're going to reform your catalyst. Not too bad, but it ends up being the OH attacks there, pushes that up, and then the O minus comes in, rips off one of the hydrogens to regenerate your catalyst. Okay. Now the acid catalyzed version is a little bit different, right? Because we can't have negative charges. Still gives the same product. Okay, so now what's happening is, because we can't have any negative charges, what ends up happening is, again, these negative character, this negative character thing is going to attack this positively charged thing. Okay, now these guys, the water can come in and attack, right, to push that away. Right, and this set of this double bond here becomes this extra set of lone pairs. So you end up with that. And then another water, because you're going to have excess water in here. Another water comes in, rips off this hydrogen to form that, plus H3O plus, H3O plus, right? Which is your which is a hydrated version of this. Okay, which is your catalyst. Okay, think of it as H plus H2O. H plus H2O. Okay, so those are your mechanisms. Okay, so you're gonna get one of these. Okay. Okay, so you're gonna need to know, right? So you're gonna have, there's a lot of reactions to know. There is a list in that in the study guide. So take a look at them. Okay, you're not necessarily going to need to know strengths of them, right? But you are going to need to know orthopara and metadirector, right? So remember with right, so with metadirectors, right, they're always going to have this right next to the ring, right? You're looking C double bond O, S double bond O, N double bond O, right? C triple bond N, right? For the orthopara, right, you're either going to have next to the ring, right? You're either going to have some sort of alkyl group, right, or it could be methyl or whatever. And then you're also going to have lone pairs, right? So you're going to have O, like OCH3, right, NH2, right, lone pairs, Br2, or Br, right, lone pairs, Cl, right, and so on. Okay, you're always going to have lone pairs. It's either some sort of alkyl group or it's going to be a set of lone pairs. Okay. Okay, so it's not necessarily good enough to know that, what the reaction does, but also where does it go. Okay, so this one here, right, this is an alkyl group, so it's orthopara. So this is ortho, right, ortho. Right, this is meta. Right, ortho is 1 away, meta is 2 away, and para is across. Right, so for here, right, you're going to get 2 products. Okay. Right, you're going to get the ortho product and you're going to get the para product, like that. Okay, for this one here, same reaction, right? But here, this is a right, C double bond O, so it's a metadirector. So you're going to add here and here, right? Right, so now the chlorine is going to go there. Right? You only have to draw one, right? Because if you put it over there, it'll just be this molecule flipped. Right? So it's going to be. So you're going to need to know this. I'm not going to give you this. I'm not going to give you this. This is what you guys need to know. Okay. Okay. So I'm going to try something a little different with the with printed products, right? So we're going to sort of matching, right? So I'm going to have this giant list of reagents, right? And you got to tell me what's on there, right? So okay, so here we go. So what puts a chlorine on benzene? Well, you need some source of chlorine, right? So with that, so you look on here to see what has chlorine on here, and well, there's a chlorine there, there's chlorine there. Well, that might do it, right? But the big thing is this one right here. So B. So what puts a chlorine on there? Cl2, and then your catalyst, your iron catalyst. Okay. Now, here we go. So bromine. Okay, so we're adding a bromine not on the ring, right? So that eliminates C, okay? But we're adding it on a carbon right next to the ring, okay? So this puts it on the ring. So what other bromines on there? We don't see any other bromines. However, we do see this. That B stands for bromine, right? Because it's in bromo succinimide. Okay, this B stands for bromine. Okay, this one puts it right on the ring. This puts it one carbon away from the ring, so it's G. Okay, this one here, what puts this sulfate group on? Sulfonic acid on it. Well, where's the source of sulfur? Right. Well, there's a sulfur here, but this puts nitrogen on it. Okay, but how about this one? Stuff like that. So there we go. And this one here, right? Stuff like that. So. Right, we're putting a fluorine on, right? So the only source of fluorine atoms in this whole thing is this one, so it better be A. Okay, so I'm going to give you this long list. I'm going to give you some reactions. You need to match them up. Okay, so I'm going to try a little different, something a little different. Okay. Now for the design of synthesis, they're going to be like this, where you're going to be adding them to the benzene. It's going to be mostly those reactions from chapter 16. Okay. Stuff like that. So not that you forget the other reactions, but this is going to be more of the speed. Okay, so you're going to get one that's a little bit more straightforward. You're going to get one that's not so straightforward. Okay, so but this would be considered more of a straightforward one. Okay, because what you want to do is you want to say, okay, what if I have this compound and can I put the chlorine on there? And then the other thing you have to consider is, what if I have this one and can I put the nitro group on there? In this position. Okay, so what if I had this compound, okay, or what if I had this compound, okay, about that. So right, so we need to think about orthopara directors, right? So NO2, right? So that if you were to redraw that would be this. Okay, so it's NO2, right? So it has N double bond O right next to the ring, right? So that's it's a meta director, right? So it would put it here and here. So if we did this, if we put the chlorine on, right, it would give us this. That's not what we want. We want it in the para position. Okay, so this isn't going to work. Okay, so let's try here. Okay. So here, right? So how do we put, right? So this one here, right? So notice how. Right, the chlorine's going to have lone pairs, right? That makes it an orthopara, right? So this ortho position, para. Now I'm going to assume that you can separate ortho and para isomers. Okay, so let's put this on in a HNO3, H2SO4, right? So here we go. Like that. Okay, so here's our product. So that means the synthesis has to go through this intermediate here. Okay, so that means how do we put on a chlorine? Right, so we have to start from benzene. Right, so how do we put on chlorine? Right, Cl2, FeCl3. So here's your synthesis here. Okay, but we have to figure out the order, not just what the chemistry is, but the order of operations. Because if we put the nitro group on here first, that's going to direct the chlorine to the wrong position. So we have to put the chlorine on first and then direct it on here. Okay. Now, if you get a question where both of these, let's say, both of these were meta directors, right? But you needed to put them para, right? What you're going to need to do is you're going to need to make one of those into a para director, orthopara director, and then convert it into and then convert it to the group you need. Okay, so you have to, sometimes you it's not just put one on and then put the other on. Sometimes you have to think about these directing group characteristics. Okay, there's some nice homework questions in there about that, but go in there. You have to take a look to see which is this. This is, is it meta? Is it orthopara on these? And how would you put the steps are going to be important here as much as the chemistry. Okay. So next up, you are going to get some compounds to name, right? So with that, so here we go. So for this one, right, we're going to have, right, so we have an aldehyde, right, so this high priority, right, so 1, 2, 3, 4, 5, 6, right, 1, 2, 3, 4, 5, 6, 7, What's the problem? Right? It has the main chain. Even if you can find a smaller one, the main chain has to include this aldehyde here. So this is actually the main chain here. Okay. So here we go. So 1, 2, 3, 4, 5, 6. So C6. Right. Which normally would be hexane. Right. But but since it's an aldehyde, we take off the E and say it's hexanal. Okay. Now we don't have to do the numbering on the aldehyde, right? Because the aldehyde's always at 1, right? But we do have this ethyl group, right? Right. So, right, we're going to say this is number 1. So it's 1, 2, 3, 4, 5, 6. Right. So the ethyl's at 2. So this ends up being 2 ethyl hexanal. Oop. If I can spell it right. Hexanal. Okay, we have a main chain that's 6 long, right, with an aldehyde in it, the Al, and then we have an ethyl group in there. Where is it connected? It's connected to carbon 2. Okay, so for this one here, right, so our main chain has to, right, we have a ketone. Main chain is going to have to have a ketone, right? So it's going to be this ring. Okay. Okay, so it's, again, it's C6, right? So that would be hexane, right? But it's a ring, so that makes it cyclohexane. Cyclohex, but then it's also a ketone, so it's cyclohexanone. Okay? So this means it's a ring. Six around, it's a ring, right? But it also has a ketone in it. Okay? But then we also have methyl-methyl, right? So from here, right, here, right? Methyl-methyl. Right? This ketone, where that is, that's going to be carbon 1. Okay, so we're going to say 1. Okay, so we're going to go clockwise and counterclockwise. 1, 2, 3, 4, 5, 6. Right, so it's going to be 2, 3. Right, but if we said this was 1 but went counterclockwise, 2, 3, 4, 5, 6. Right, so it would be 5, 6. Right, so you add them up. Right, so 5 versus 11. Right, so these are going to be the numbers you want. Okay, so it's going to be 2, 3, dimethyl. Okay, cyclohexanone. Now, you could say 1 cyclohexanone, and that'd be totally fine. It's sort of assumed with the ring that it's understood that the ketone is going to be a carbon 1. If you want to put 1 cyclohexanone, totally fine. I'm not going to catch you wrong on it. Stuff like that, but you don't need it in this case. For rings, you don't need it. Okay. Now for this one here, right? So 1, 2, 3, 4, 5, right? There. Okay, so 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5. 1, 2, 3, 4. 1, 2, 3, 4, 5. Right? Remember, we have the ketone, so it has to include the ketone, right? So this is, I'll just do this one, right? You can either do 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Doesn't matter. But it's C5, right? So it ends up being pentane, right? The base is pentane, right? But we're going to take off the E and say this is pentanone. Okay, now we have this, the methyl and ethyl, right? Methyl and ethyl. But we also need to say where that ketone is, right? Where in the chain is the ketone, right? So we're going to have, we have to number that as well. Okay, so with ketones, right? So it's the end closest to the end closest to the ketone. That becomes 1. So it's 1, 2, 3, 4, 5. Right. So our ketone's at 2, and both of these are at 3. Okay. So it ends up being, right. Ethyl comes before methyl, so it becomes 3 ethyl. 3 methyl. 2 pentanone. Right? We have a main chain of 5. Main chain of 5. We have a ketone, right? The O and E. Where is it? It's at carbon 2. We have a methyl group. Where is it? It's hanging off of carbon 3. We have another ethyl group. We also have an ethyl group. Where is that hanging off of? Oh, that's also hanging off of carbon 3. Not too bad. Okay. Now for this one, right? Mark our carbons, right? Okay, so we have an aldehyde versus a ketone. In this case, the aldehyde has a higher priority, so we have to go through this one, right? So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, right? 1, 2, 3, 4, 5, 6, 7, 8. But we have to include that aldehyde, right? So this is going to be our main chain. So even though there's another 8 carbon chain in there that we could go through, we have to. It needs to go through. Right here. It doesn't include the aldehyde, which we have to do. So 1, 2, 3, 4, 5, 6, 7, 8. So C8, right? So that would normally be octane. Right? Include the knock off the E, and it becomes octanol. Okay. Now this ketone becomes just a regular side chain, and we call that an oxo group. Okay, and then we also have the ethyl. Okay. Again, the aldehyde is carbon 1, right? So it's 1, 2, 3, 4, 5, 6, 7, 8, right? So it's going to be 3 ethyl, 4 oxo. Okay. So to name it, right, the ethyl comes for the oxo because it's alphabetically. So 3 ethyl, 4 oxo, octanol. Right? We have a main chain of 8 long. We have an aldehyde at the end, or I should say at the beginning, right? At carbon 1. We have a ketone group, the oxo. Where is it? It's at carbon 4. Right? We also have an ethyl group. Where is it hanging off? It's hanging off of carbon 3. So here you go. Okay, so reactions. We're also going to do some predict the product kind of questions, right? So for Des Martin, okay, remember we're going to take one CH and convert it into a new CO bond. Okay, so we're interested where that oxygen is, right? So okay, so this carbon, that carbon there, right? It has 2 carbon hydrogens and 1 carbon oxygen. Okay, for Des Martin, we convert one of those into that, right? So our final product is going to be 1 CH and 2 COs. Okay, so our product is going to look like this. How do we put two carbon oxygen bonds on it? We make it into an aldehyde, like that. Now for dibol, okay, we're going to convert 1 CO into one CH, right? So it's the opposite. But notice how we have two sets of oxygen, 2 carbons with oxygens on it, so we're going to have to work on both. Okay, so here, right, we have 1 carbon hydrogen and 2 carbon oxygen, right? So we're going to convert one of those into. So this side of the product is going to have 2 carbon hydrogen and 1 carbon oxygen. Okay, and this side here, right, we have 0 carbon hydrogen and 3 carbon oxygen, right? So we're going to convert one of those. So our other product is going to be 1 CH, 2 COs. Okay, so this side is going to have 2 carbon oxygens, 1 carbon hydrogen. This side here is going to have 2 carbon hydrogen and 1 carbon oxygen. Okay. Now for this one, we convert all COs or all CHs into COs. Okay. Okay. So again, we have 2 carbons with oxygens on them, right? So we're going to have to deal with both of them, right? So this one here, right? We have 1 carbon hydrogen, 2 carbon oxygen, right? So that means over here we're going to convert all of those. So it's going to be 0 carbon hydrogen and 3 carbon oxygen, right? Here again we have 2 carbon hydrogen, right? 1 carbon oxygen. Again, we're going to convert all those, so we have on this. I should do that in blue. So this side again, we're going to have 0 carbon hydrogen and 3 carbon oxygen, right? So I should mark this in blue. Okay, so we have three carbon pieces, right? So how do we make 3 carbon oxygen bonds? Right, we make this into carboxylic acid. Same thing on this side, carboxylic acid. So we have the dicarboxylic acid. Okay. Now for this one, right? So we have water, right? we have a ketone, right? So it's going to add there, and it's going to be an OH plus what you attacked with. OH plus what you attacked with. In this case, yes, I mean, I know we added H2O, but we're going to rip off one of those hydrogens to leave an OH behind. Okay, again, with this one, right, we have a ketone plus water, right? But, we'd have this OH in line with it. So in this case, we burn this carbon-carbon double bond first, and so you end up adding it here. So the OH goes inside, and this H comes on that side. But you end up going, right, so this is so if you count 1, 2, 3, 4, right, 1, 2, 3, 4, this is a 1, 2 addition, this is a 1, 4 addition, so 1, 2, 3, 4, it adds 4 away from this oxygen, right, so 1, 2, 3, 4, right, this one adds 1, 2, 1, 2. Okay, so just be wary of that double bond, if there's a double bond in next to the ketone there. Okay, so for these reactions, right, we're going to be converting, right, so we have an aldehyde, we have an amine, right, so here, right, we have one NH bond, right, so that means our product can only have one CN bond, okay, so it means the double bond that's formed with this has to be over here, this one side, right, so if you only have one of these that you can form, that means that the double bond has to be off to the side. So that means our final product it's a single bond, right? But the double bond has to be off to the side. Okay? But here, right, we have two nitrogen-hydrogen bonds. So that means we can make two carbon-nitrogen bonds in our product. Right? Chlorine, bromine, right? So this one, right, we lose the hydrogens, right, so for that, and for here we can make the two carbon-nitrogen bonds to make the imine. Here we only had one nitrogen-hydrogen bond, right, so we can only make one carbon-nitrogen bond here, so that means the double bond had to be off to the side. Here we have enough nitrogen-hydrogen bonds that we can make the double bond in between the carbon and nitrogen. Okay, so for here, right, so HCN, right, so that's actually going to add there to make HCN. Okay, that's going to be your intermediate, right, but if you add water and acid, okay, basically what's going to happen is, right, this is a carbon-nitrogen triple bond. What you're going to end up making is you're going to substitute the oxygen, you're going to convert CN bonds into CO bonds, right, so 3, 3. And so how do you make a carbon with 3 oxygens on it? You make it into a carboxylic acid. Okay, and the nitrogen goes away. It ends up being NH4+. Okay, so this one puts on makes a cyanohydrin, right? So puts on, right? It's an OH plus what you attacked with. In this case, it's cyanide. And then this one here hydrolyzes it away. Okay, and it converts CN bonds into CO bonds to make the carboxylic acid. Okay, and then the nitrogen goes away. Okay, last one. Okay, so again, in this case, right? So you just have this kind of comes along for the ride, right? So we're going to take 2 carbon-hydrogen bonds and make this into 2 carbon-nitrogen bonds. So that's good, right? So we can make it just like that, plus whatever this comes along for the ride in H2. So that's it. Now, if we have if we put KOH in here, then it converts it into the Wolff-Kishner. Now for that, what ends up happening is we erase that, and so you end up with just that. We convert a C double bond O into a CH2. So essentially, on the skeletal structure, it looks like we've just erased that. Okay, but we've added hydrogens there. Okay, the last one, this is the Wittig. Okay, and what ends up happening is where there's this carbon minus, that replaces the oxygen, and everything, all the other carbon, the phosphate goes away and actually carries the oxygen away with it. This stuff here kind of comes along for the ride with this one here, so you end up with, right, and then CH like that. Okay, so where the negative charge is, that just replaces that oxygen, and all the rest of the stuff just kind of comes along. Okay, the oxygen, this phosphine here, that actually grabs the hydrogen and that goes away. So like that. So okay, so keep practicing and good luck.